In this video, we're going to look at some different forces, and it's from the 7K topic that you learn about in Year 7. The most important thing is that forces are measured in newtons, and they always have a size and a direction. So in this case, this arrow is showing a force of 20 newtons to the right, and that's normally how we draw forces, with a line and an arrow and with some value, in this case 20 newtons, showing the size of that force. There are three basic types of forces. We can have a push force, shown by a footballer, a rugby player kicking a ball and giving it a big push. We can have a pull force, shown here by the guy trying to pull a great big crate of rocks. And we can have twist forces, shown here about wringing out a towel and twisting that towel to get the water out. And those forces tend to do three different things. They can either change the speed of an object, like this football going from 0 meters per second to maybe 10 meters per second as it's kicked through the air. They can change direction. This sack or trolley of rocks was stationary and now it's going in a particular direction. Or it can change shape. We used to have a flat towel, but as we've wrung it out and twisted it, we can change the shape of that object too. And there's loads of different types of forces. As you can see here, we have some friction caused by the wheels running against the road surface, causing a little bit of friction. We have air resistance by the air bashing against the top of the parachute, slowing down the parachuter. Similarly, we have water resistance. As this jet ski slides across the sea, there'll be water resistance between the bottom of the jet ski and the waves. We have upthrust and buoyancy. This is shown by the boat being not sinking as the water pushes back on the boat to keep it afloat. We have gravity or weight. As we can see here, this apple falling from the tree due to its weight and the force of gravity. We have magnetism. Magnets can attract magnetic materials. We have thrust from an airline jet engine pushing the aeroplane forward. We have tension in the rope. As these two boys are pulling on the rope, there'll be tension within that rope. We have an applied force, as a boy kicking a football. We have a reaction force, and this one's really interesting. This is where the table is pushing back on the books to stop those books falling. Those books obviously have some mass and therefore some weight and are pushing down on the table, but the table is pushing back, giving us a reaction force. So we have the force of gravity going down, but we have a reaction force from the books pushing up. And these two arrows I've drawn at the same size because these two forces are equal because the books aren't moving. And finally, we have static electricity. This is the force that charged objects can have. Now, the majority of these forces that we've got here are contact forces. You have to be in contact with the object for the force to work or the force to be applied. So friction, air resistance, water resistance, upthrust, thrust, tension, applied force, and reaction force. They are all contact forces. Whereas we have gravity and weight, magnetism, and static electricity. These are all non-contact forces. With these, the objects do not have to be touching. The apple isn't touching anything, it's not touching the earth, but it is still falling towards the earth. And we know that magnets can attract magnetic materials even when they're not touching them. We need to look at this idea of force diagrams and think about how we can draw these forces in these particular scenarios. So let's think about a football just after it's been kicked. Now, I always like to start off with a box. And we know that this is a football, so I'm just going to write ball inside the box. Now, it's just been kicked. So there'll be a big applied force to the ball just after it's been kicked. And there may be just a tiny little bit of air resistance also acting on that ball just after it's been kicked. But this arrow is much larger than this arrow, so the ball will accelerate. It will move forward, accelerate. And we can say it will accelerate left, as I've drawn it here. In the next example, we can think about this aeroplane in flight. And again, I like to start off with a box, make my diagrams really, really simple, and think about a plane. Now, there may be some thrust pushing that plane forwards. And there will be some air resistance applying to the plane as it flies through the air. Air will be bashing against this plane as it flies through. And there will also be some upthrust, or maybe even lift from the wings. And there'll obviously, because the plane is extremely heavy, some weight forcing the plane down. Now, I've drawn all these arrows of very similar size, and if you think of them as pairs, this upthrust and weight pair are the same size. So this means that the plane will not be moving up or down. It's going to stay in the same position. And similarly, I've drawn the thrust and air resistance arrows at the same size, and that just means that the plane will continue at the same speed. It's not going to get any faster. It's not going to get any slower. It's certainly not stopped, but it'll just be moving at the same speed. So if we have matching or balanced forces, that means that the object stays at the same speed. And in our case, it's this aeroplane at the same. And in our case, it's this aeroplane. It will be just flying through the air, not accelerating, not getting any faster, not slowing down, not getting any slower. And finally, let's look at this skier going downhill. Now, this diagram is slightly more tricky because I've put the skier on a slope. There is still weight, and that still acts straight down. And there will be some friction on the slope holding the skier back. And there'll also be a force from the snow or from the slope pushing back on the skier. And that's at right angles to the slope. So we have this reaction force. So slightly trickier, but we always remember that weight acts straight down, and the reaction force, if I draw the dotted line here, is at 90 degrees to the slope. And friction always is acting against the motion, so it's going in the opposite direction. So the skier would be moving in this direction. I hope you found that useful, and hopefully your thinking around forces has improved a little bit.